Okay, welcome back. So this is the video on simple cell. So recall, electrolysis is the point of electrolysis is that we want to run an electric current through a solution, and in doing so, we can cause a non-spontaneous reaction to occur. Okay, so what is non-spontaneous? It means that if you just let it be, nothing will happen. It's like if you put the ball here, it will not spontaneously roll up and go down by itself. You need to put in some energy to push it up. Okay, so electrolysis is to give it that push with the electrical current. Okay, what happens? Electrons flow from the negative terminal to positive terminal of the battery. Cations move to the negative electrode, and ions move to the positive electrode. This one we've learned before. Then, our question to you: how do batteries produce electricity? Okay, ever wonder why this is called alkaline battery? Why this lithium-ion battery? You don't know, right? Okay, so simple cell. It is a device that can convert chemical to electrical energy. It is also known as a galvanic cell, a voltaic cell, or electrochemical cell. Okay, there are a lot of names to simple cell. Not so simple after all. Okay, can you take down all the names? It's made by placing two different metals. So two different metals in contact with an electrolyte. So why do we need two different metals? Okay, here is a voltaic cell, or a simple cell or galvanic cell. Okay, predict what do you think will happen when the metal strips here, copper and magnesium, connected to a light bulb, are immersed in copper 2 sulfate solution, but they are not touching. Okay, what do you think will happen? Oh. Okay, so recall that the anions lose electrons to become a gas. Reactive metal electrode lose electrons to become cations, and cations gain electrons to become metal deposits. So these are the compounds present that can be oxidized and reduced. Okay, why is it that the metals are placed here and not here? Because remember, metals can't be oxidized further. Okay, metals can be reduced further. What was I talking about? Okay, metals can be oxidized because they can lose electron to become more positively charged. Okay, but they can't be reduced because they can't gain electron and become negatively charged. So, when water is present, we also need to consider hydroxide and hydrogen ions. Okay, so can you think of this, the side that's oxidized and the compounds that can be reduced? Which will be preferentially oxidized and which will be preferentially reduced? Hint: oxidation is to lose electron, whereas reduction is to gain electron. Okay, so which will lose electrons more easily? Which will gain electrons more easily? Okay, so let's look at the answer. What will happen is that magnesium is the one that will be preferentially oxidized because magnesium is more reactive than, okay, so again, what do we have? We had magnesium, we had copper, sulfate, and hydroxide. Okay, so remember I said before that if you have a reactive electrode, then that will take precedence over the anions, definitely, because they can give out the electrons more easily. So between magnesium and copper, which one will give electrons more readily? Okay, this has got to do with your reactivity series. Remember, the more reactive the metal, the easier it loses electron. But does this keep happening to me? Okay, so more reactive equals lose electron more easily. Okay, we recall that magnesium was above copper in the reactivity series, making magnesium more reactive. That's how you can tell that it can lose electrons more easily. Okay, so over here, what will you observe? You will see that magnesium becomes smaller. Okay, then we see pink or brown deposits on copper. Now on the other side, why is it that copper 2 plus ions are the ones that's being reduced? So if we recall, on the reduction side, we had copper 2 plus, we also had hydrogen ions. Okay, of the two, based on the electrochemical series, copper 2 plus is the one that you will be reduced. Okay, so we have these two half equations, and because magnesium is the one giving electrons, okay, this is the one taking electrons, there is a flow of electrons, making the light bulb lights out. Okay, so the overall equation is Cu2 plus gives you magnesium, plus magnesium gives you magnesium 2 plus and copper. Okay, I think it's too late in the office already. I a bit sad, I want to sleep. Okay, anyway, so what's the direction of flow of electrons? Just now I mentioned it should be from magnesium to copper. So the flow of electron is like this. So what is the flow of conventional current? We call that the flow of conventional current should be opposite to the direction of electrons. So the conventional current flows from copper to magnesium. Okay, now the question to you is, which side is the positive electrode and which side is the negative electrode? Why? Okay, I think maybe you saw a glimpse of it just now. Copper is the positive electrode and magnesium is the negative electrode. Why is that so? Okay, you can think of it as, first, okay, the negative terminal is the one that supplies electron. Correct? The negative terminal of a battery is the one that supplies electron. So in this case, since magnesium is the one that's giving out electron, it is the negative terminal. Okay? The positive terminal receives electron. Okay? Second way you can think of it is that, okay, the electrons flow from magnesium to copper. This electron flow. Okay, so flow of conventional current is copper to magnesium. Conventional current. Right? I still remember my physics. So we recall that conventional current always starts from the positive terminal to the negative terminal. So this is how you can assign the positive and negative terminal for a voltaic galvanic simple cell. Okay, again, cathode and anode, their definitions did not change. So can you identify which is the cathode and which is the anode of this setup? Okay, I already tell you reduction is cat, oxidation is the ox. Okay, so as this happens without intervention, it is a spontaneous reaction. You do not need to put battery or what. This is the battery itself. Okay, it is the one generating the electron flow itself. Okay, so Brenda has a good question. Okay, Brenda is confused. Okay, I thought that since magnesium is more reactive than copper, it will displace copper from its solution immediately when it touches the solution. Why will the electron pass through the wires to the other side for copper 2 plus to gain the electrons at the copper side? Okay, so why not directly at the surface of magnesium? Okay, so this is what Brenda meant. Remember we learned before that a more reactive metal displaces the less reactive metal from the solution. Okay, so copper should be forming at magnesium here. and then the solution should get lighter in color, right? That's what we learned before in the metal reactivity series. I also showed you the video on it, right? So the answer is that it is true that at the surface of magnesium, the displacement reaction with copper 2 plus ions will occur. But at the same time, a small amount of electrons will still pass through the wires to the other side to pass to copper 2 plus at the other electrode. So what happens is this. There is a transfer of electrons to the Cu2 plus in the solution directly here, but some of the electrons are also moving through the solution to the copper 2 plus here to be given to the Cu2 plus here. Okay, so copper will be deposited on both sides, okay, in real life. Okay, so therefore, don't you think it's kind of stupid? It's like you're wasting electrons and you're generating less current than we should be. Because current is about the flow of electrons, right? So if there's more electron flowing by at per second, then there's more current, we can do more work. Okay, but here, some of the electrons are directly given to the solution here. So these electrons are not passing through the wires. Therefore, in real life, we do not have that kind of setup. We have this kind of setup where we put the two metal in separate solution. Okay, copper metal in copper 2 plus solution, magnesium metal in magnesium 2 plus solution. Okay, because the metals do not react with their own metal solution. So therefore, that prevents any displacement reaction from occurring or any unwanted side reactions. Okay, it is connected by what we call a salt bridge. Okay, this salt bridge is to maintain net neutrality of the solution. Why did my words keep disappearing? I must solve this mystery. Okay, to maintain net neutrality of solution. Okay, what does it mean? This salt bridge has, like, let's say sodium sulfate inside. Okay, what happens here is because a lot of Cu2 plus is being used up, okay, this side start to become more and more saturated in your sulfate ions, okay, and becomes increasingly negatively charged. So what happens is your sodium cation will move in to balance out the charge on the solution. On the right hand side, because your magnesium keeps becoming magnesium 2 plus, okay, so over on the right hand side, okay, it becomes increasingly positively charged. So your sulfate ions will start to move in to ensure that the solution here is also neutral. Okay, this way, the metals do not react with their own salt solution and ensures that the only electron flow is through the circuit. But this is not in the O-level syllabus. We just generally try and look at what will happen if we assume that all the electrons flow through the wires. Okay? Assume. So, can you try and predict what will happen when aluminium and iron is placed in a solution of sodium nitrate? Okay, let me just draw it up for you. What do I mean? So here, let's say I have iron, and here I have aluminium. Okay, this is a solution of sodium nitrate. Okay, what do you think will happen? Which is the cathode and anode, and what is the direction of electron flow? Okay, first decide what is oxidized and decide what is reduced. Okay, so what are the compounds present that can be oxidized and reduced? Aluminium, iron, nitrate, and hydroxide. Reduction, we have sodium and hydrogen ions. Okay, between aluminium and iron, okay, again, we ignore the anions because we have reactive metal electrodes. So when we are looking at the two metals, aluminium is the one that's more reactive than iron. Hence, it loses electron more easily. Okay, so that's the one that will supply the electron. So over on the other end, we have sodium ion and hydrogen ions. Now, hydrogen is way below sodium in the electrochemical series, so hydrogen is the one that will be discharged. So here are the half equations, and here's the overall equation. Actually, I wanted you all to try writing it yourself, but then I forgot to do animation for this part. Okay, never mind. So, what are observations? The aluminium metal should become smaller and smaller. Over at the other end of iron, we can see that effervescence is observed. Colorless, odorless gas evolve, extinguished letters mean with a pop sound. So, we have the which side is positive and which side is negative. Sadly, I've drawn it for you. Okay, aluminium here is negative. Why is that so? Which is the side that's supplying electrons? Your aluminium. Okay, which is the side that's getting electron? Over at the other electrode. So the flow of electron is as such. Therefore, what am I drawing? Okay, my arrow is a bit weird. Okay, it should be flowing this way. Okay, so it moves in this direction. So since aluminium is the side that's supplying the electron, it is the negative terminal, and iron is the positive terminal. Okay, this is the oxidation side, that's why it's the anode. This is the reduction side, this one is the cathode. Now, can you go back and look at the notes for the electrolytic cell? You see the notes? Okay, notice that your anode, right, here is always the negative terminal, and here the cathode is always the positive terminal. Look at your electrolytic cell. What do you see it being? Okay, is your anode also at the negative terminal, or is it at the positive terminal? Okay, now simple cells can also be used to determine the relative positions of the metals in the reactivity series. So the further they are, the greater the voltage. So what is the definition of voltage? Okay, I leave it to your physics teacher. Okay, no current will flow if both electrodes are made of the same metal. Does it make sense? Now, what is actually driving this reaction is because the two metals, they have different tendency to be oxidized. Okay, so let's see an example. If your positive electrode is copper, your negative electrode is always the more reactive metal. Now, if you have copper versus copper, there's no voltage. Okay, whereas if we compare silver and copper, copper being the one that's more reactive, it will become the one that's supplying the electron. Okay, so remember that the negative electrode is the one that supplies electron. Okay, hence it is also the place where reduction lose electron, gain oxidation takes place. Okay, and this oxidation is always of the more reactive metal. Okay, so you can see that the further the distance, the greater the voltage difference. Okay, so please stop calling me cute zebra, no cute. I like her. Okay, let's just I like Hua Chong. Okay, so up to there. So we see that we have magnesium and copper. The difference is 2.7. We have zinc and copper. The difference is 1.10. So actually, if you join different metals together and we look at the voltage, you can actually tell how far away are they in the reactivity series. Okay, so actually these can help you place metals based on their reactivity series. Okay, like for example here, we know that magnesium must be further away from copper than it is from zinc. So magnesium should be higher in the reactivity series as compared to zinc. Okay, so going back to the question of how do batteries produce electricity. Okay, so this is actually your zinc alkaline battery. So what is happening here? We have the zinc anode. Okay, anode meaning is the oxidation side. So what happens is it will lose electrons. Lose electron. Where does it lose it to? There's the manganese oxide cathode, which will gain those electrons. Okay, to your manganese oxide cathode and be taken out. So this is actually called alkaline battery. Why? Because notice that your hydroxide ions are being used up in the first reaction. Okay, so first for zinc anode to even be oxidized, it needs the presence of hydroxide ions. But at the same time, we see that for the second reaction of the reduction reaction, hydroxide ions are regenerated. So in this manner, hydroxide ions are never run out. Okay. This is also why it's called the alkaline battery. So overall, we have this equation. Remember that the negative terminal is the one that's supplying the electrons. So you all are not in groups, but you can still go back and think what is the similarity and differences between a simple and electrolytic cell and present it in a table. I think there's one blank page for your notes at the back, so you can draw a table there. Okay, you can also try and draw a setup where we have a simple cell that's used to drive the electrolysis of another substance. Okay, this is quite hard. Again, a simple cell is like a battery that generates the current. Okay, electrolysis requires a battery to drive reaction. Okay, so how can we combine these two types of cells together? Okay, that will be your homework. Try and think about this. Okay, so here's some true or false question. True or false? Only ionic compounds can be electrolyzed. Answer is true. Okay, only ionic compounds can be acted as an electrolyte. An anion and an anode have the same kind of electrical charge. Is this true? False. Okay, an anion has a negative charge. Okay, an anode can either be positively charged or negatively charged, depending on what type of cell it is. For an electrolytic cell, okay, is the positive terminal. For the what's the other one called? For the simple cell, we set the negative terminal. Next, reaction in electrolysis are redox reaction. True or false? Okay, true. They are always about redox. In aqueous solution, the ions of metals high in the reactivity series are not discharged. True. Okay, when the metals that are high in the reactivity series, they are not easy to be reduced. Okay, they tend to like to be in their ion state. Okay, the electrons in electrolysis are always inert. True or false? Okay, of course false. Okay, I teach you some of the reactive electrodes already, like copper, like lead, silver, zinc. Okay. The further apart in the reactivity series the metals in the electrical cells are, the larger the voltage. True. Okay. This is the end of my video. Thank you for watching.